Welcome everyone. Today we're just going to look at one example calculating double integrals using polar coordinates. And the example we're going to look at is this volume calculation. We're going to find the volume of this solid that's bounded by the plane z equals 0 and the paraboloid z equal to 1 minus x squared minus y squared. So right away, the tip-off here that we might be interested in using polar coordinates is we see this x squared plus y squared. So we should immediately be thinking, all right, there might be some kind of circular action involved here. All right, so let's think about first just what this surface and what this object looks like, and then we'll work on setting up the integral. And when we look at this, we're tipped off that this surface is a paraboloid. Now, how we can see that is if we look at just this part of the equation, z equal to 1 minus x squared, this is an upside down parabola that's shifted up 1 unit, and it opens up in the x direction. So let's get a little sketch of what's going on here. So we might have an upside down parabola in the x direction. And then if we look at the other part of the equation, z equal to 1 minus the y squared, well, then we have a upside down parabola shifted up 1 unit that opens up in the y direction. So we end up with something like this. And let's throw some axes in here just to... Now where this high point happens, the highest point of this parabola, this is going to happen when at the origin. And we can tell that because these x squareds and the y squareds here are negative, so these are always going to be subtracting something away from 1. So the highest point happens when both x and y are 0. So that's the kind of the peak here of our paraboloid. So we have our origin, which is giving us the high point, and then maybe here's our y-axis, here's our x-axis. No, I said them reversed, but we got to get the right order here. And then the z-axis is just pointing straight up. All right, so this is the surface z equal to 1 minus x squared minus y squared. Now z equals 0, that's just the xy plane. So what we want to do is we want to figure out where these two, to get started, we want to find where these two surfaces intersect. So we want to find the curve of intersection. And when we have the equation for two surfaces, z equals, we can just set these two equations equal to each other. Or another way to think of it, if we have z equals 0, we can just plug 0 in for z. So we're just setting these two equal. And what we get is so we're just going to plug that into our other equation, z equal to 1 minus x squared minus y squared, or we set these two equal to each other, and we end up with the equation 0 is equal to 1 minus x squared minus y squared. Now this is a circle of radius 1. And to maybe see it a little bit better, you could get the x squared and the y squared over to the other side, so then you have x squared plus y squared is equal to 1. And so what we're seeing is we have this equation now that's giving us the curve of intersection, and the paraboloid kind of opens up above that. And so our region D here that we're going to be, or our region R, whatever we want to call it, that we're going to be integrating over is this circular section of the xy plane. So this is like, so our solid here is everything contained inside this paraboloid, and this circle on the xy plane is like the shadow of that surface or that solid projected down onto the xy plane. All right, so we want to describe this circular region. So we'll call this region D. So how do we describe this? Well, we want to describe it in polar coordinates. And the reason is because we could describe it in regular rectangular coordinates, perfectly fine to do that. The issue is this is part of a circle. And maybe to help, let's actually draw it on, let's just draw the xy plane. So it always helps. Just draw the xy plane. Just to kind of get an idea of what's going on. So we have our x-axis, our y-axis, and then we have that unit circle of radius 1, going around the origin. And here's another view of that region D. It's everything inside this circle, including the edge of the circle. So we got another view here of our region D. And for circular regions like this, it's usually better, try and describe it with polar coordinates. So what we want is we want all points r comma theta, and we want an inequality for r, and we want an inequality for theta. All right, so first of all, what's an inequality for r? Well, if we look at all the points here, pick any point inside this circle or on the edge of the circle, the smallest radius we could have is if we pick the point right at the origin, and the largest radius we could have is if we picked a point right on the edge of that circle, which is radius 1. So the r value here is going to be between 0 and 1. Now what about theta? We want an inequality for theta here. And remember, theta measures the angle from between the ray formed from our point and the positive x-axis. So we're looking at we're thinking of the positive x-axis as where we're starting our theta measurement. And you want to think of this as almost like a sweeping motion as we rotate counterclockwise around the origin. And so if we start at this positive part of our x-axis and we kind of rotate this around, we go completely around the circle. We just sweep out the entire circle, and then we get back to where we started, and we stop. We don't want to retrace our steps. So theta equals 0 gives us the positive x-axis, and if we go one complete time around the circle, 2 pi, 360 degrees, but we're using radians. All right, so there is our description of our region R. And now we're ready to set up the double integral. So the double integral here to calculate the volume is going to be the integral over this region D of, and when we do this, we're finding the amount of space underneath this paraboloid. So the function we integrate is the equation for that paraboloid. It's the top surface, which is that parabolic shape, minus the bottom surface, which is just that flat section of the xy plane. So normally it's the top surface minus the bottom surface, but in this case, the bottom surface is just z equals 0. So it's not going to contribute anything to our function. So our integral here is going to be 1 minus x squared minus y squared. And again, that's just our top surface here. Technically, there's a minus 0, but we're not going to worry about that because it doesn't do anything. And then we have our double integral differential dA. All right, so now we said we're going to convert this into polar coordinates. So now let's set it up as an iterated integral. And when we do this, we have to convert all of the x's that we see. We have to convert all of the y's that we see, and then we have to convert that differential. So let's remember, when we have an x, instead we're going to plug in r cosine theta. When we have a y, we normally plug in y r y is equal to r times sine theta. And then that differential, kind of the important one here. That is r dr d theta. So we got to convert that as well. And we have that important little r term there. So it's not a nice, well, it's still a nice conversion, but we have that extra little piece that we have to remember. All right, so when we look at this, we could rewrite this function just a little bit. So we could think of this instead as 1 minus x squared plus y squared. And when we see an x squared plus y squared in our function, property of our trig identity, or our conversion from polar coordinates, and actually let's go back up. What did we look at yesterday? We looked at, where was it? I think the first thing, just remembering our polar coordinates. So the usual conversion back and forth between regular, rectangular, and polar coordinates, we normally use these. We also have this little gadget that can be very helpful. So we don't have to always go back to trying to do cosine squared plus sine squared is equal to 1. If we see any x squared plus y squared, just simplify it to r squared. And that's what we're going to do. So that x squared plus y squared here, we could plug these in. Perfectly fine to do that. And then you want to simplify it down. But let's replace that with a r squared. So when we do the conversion here, we're going to write this volume then as an iterated integral. And so the function will be 1 minus r squared. And our differential dA is going to become r dr d theta. And the way I have these differentials written out, we're going to do the integration for r first. So that means the limits for r have to go on the inside. And then I have d theta last, so we're going to put our limits for theta on the outside there. And again, don't forget, we have that little r term. So it's easy to kind of lose track of this one. All right, so now we're ready. Let's multiply our function out. So when we do that, we get the integral from 0 to 2 pi, the integral from 0 to 1, and then we have r minus r cubed, dr d theta. And now we could just go through standard iterated integral business here. One kind of helpful thing sometimes happens is we can, because this inner integral doesn't have any thetas, we can actually split up our integration here. So we can actually write this as the integral from 0 to 2 pi d theta times the integral from 0 to 1 of r minus r cubed. And this is Fubini's theorem. That's special case. So if we can factor our function into just r terms and then just theta terms, we can split up the integral and do just the theta terms and just the r terms. Now in this case, the theta terms, we could think of this as just like a constant 1. So, we usually can't do this, but sometimes we can. And it just makes things a little bit easier if we can. So always be on the lookout. So now if we can do each of these integrals separate. So let's do this r integral and our theta integral. So the antiderivative for our theta integral will be just theta. And we're evaluating that from 0 to 2 pi. And then the antiderivative for r minus r cubed is going to be 1/2 r squared minus 1/4 r to the 4. And we're going to evaluate that from 0 to 1. When we plug in and do the subtraction here, we get 2 pi minus 0, so we get 2 pi. And when we plug in and do the subtraction over here, we end up with 1/2 minus 1 over 4, well, minus 0. Probably shouldn't have wrote the minus 0. What are you going to do? And if we simplify this down, we end up with 2 pi times 1 over 4, which is pi over 2. All right, so it can make this a little nicer if, it doesn't save too much work in this case, but always be on the lookout when you can try to split things up like this. Now, if this function had like a sine theta thrown in, so if we had r minus r cubed sine theta, we wouldn't be able to do this nice little technique here. So the only reason why we were able to do this is because technically this is factored, and we have all the r terms and all the theta terms kind of separated, and we can factor it like that. And this is the idea. So the tip off here that we would probably want to use polar coordinates rather than just regular Cartesian coordinates here is, again, our region D that we're integrating over is a circular or part of a circle. So polar coordinates kind of lend themselves to that. All right, so we'll try a few more examples in class, and we'll see you then. Bye-bye.